So for this now, let me scroll down. The group 2 elements, right, of the first row, well, and the first row transition elements exhibit similar characteristics and distinct differences to their physical and chemical properties. Table 2 provides information. Sorry about that, let me scroll up. Table 2 provides information on the first ionization energies, right? Atomic radii, electronic structures of the atom, and oxidation states of some of the elements. So we have magnesium, calcium, strontium, vanadium, chromium, manganese, iron, and cobalt. So what is the electronic configuration of magnesium?
H2 with no. Is it the first? Oh, neon.
Okay, so use neon. All right, so neon. Okay, so why? Well, I wouldn't even ask why we use neon. So we use neon, right? And then we continue to use what now? 3s2, no so.
Yes, sir.
Calcium would be what? Argon. Then what?
Forest.
4s. Lovely. And what would the EC of strontium?
Sir, we are going to get a periodic table.
You don't need a periodic table for this. What are you talking about, man? You don't need it.
Sir, full of time to remember all of this. We
Hold
need a
on.
periodic table.
Hold
The
on.
booklet has the thing on it. So yes, guys, we'll be fine.
No, but you what? You don't
Yeah.
need
Mr.
this.
Scott,
All right, strontium.
Mr.
Sir,
Scott,
what? I don't remember the whole of the mass number them for every element.
Okay.
Jay,
Go ahead. Go ahead. Go ahead.
is forest and 3D the only anomaly in relations to the energy level, or it would always happen like that going up?
There's the only anomalies that you will see at Unit 1 chemistry. That's the best answer I can give.
Me not hear what you say.
They're the only anomalies you'll see at this level of chemistry. Okay, what? Okay,
Okay.
okay. So,
Sir,
strontium, go ahead. Go ahead.
is the first one for magnesium, is that the electronic configuration considering the +2 charge?
Oh, no, it isn't. Or we're looking at its oxidation states. Did it ask us to consider the +2 charge? I don't think so.
If it was like that, they would put it over the other side where the element is. They want us to write oxidation state too.
The most common oxidation state. What is the EC of strontium? Guys?
Sir, the data booklet must contain a periodic table, you know. That them are serious.
Okay, yeah. So it
Always
must
come to it, I think.
Okay, so what was the strontium, guys?
Sir, 5s2.
5s2. Why you don't need a booklet is because, right, if magnesium, calcium, and strontium are in the same group, they must end the same way. So you do not need one, right? So that is what we basically say, right? You do not need one generally, but you're going to get one, so it doesn't matter really. So what we have now, argon. For vanadium, it would be argon, and then you should have a 3D3 4s2, right? So you're gonna have a, well, in this case, how would we write 3D3? 3D3, and then we're gonna have 4s2. And then for our chromium, we should
Sir, why did they write it like
because that's how you should write it, but that is not how it works. If you get what I'm saying, it adds from 4s. Could you have me for a second? All right, so it adds from 4s, right? But really and truly, it's 3p then 3d, then you write your 4s. So this is the notation that they're using. They're following the notation, right? So therefore, we shall follow the notation as well. For chromium, we know it would be 3d5 and should be 4s1, right? For our iron, what would our iron be? What would our iron be? Iron is 26, therefore it would be argon 3d6 4s2. So it should be argon 3d6 e6 4s2, right? And then our cobalt specifically, we know that our cobalt is regular, it's not an anomaly, right? So it should be that 3d, what would it be? 3d cobalt is 27, therefore this should be 3d7 4s2, right? And let's look at this now. Calcium's oxidation state is usually +2. Strontium oxidation state, is it +2? Is strontium's usual
yes, sir?
alright, +2. Right, vanadium has how many oxidation states we're talking about now? We're talking about the +2. We're talking about the plus. Is it +4? +4 is more stable than +3. But let's go. So +3, we have +4, and we have the +5 oxidation state that we could talk of. But which ones are the most stable ones? Generally here, I'll just remain with those. They have multiple oxidation states. Chromium, our most common ones that we see at Cape here are these two. Right, manganese, the most common ones that we see at. Should I just write the most common ones that we see at Cape? We see +2, right?
Yes, sir. Just right.
We see plus. We don't technically see +4 so often. We see +6, and we'll see +7. Right, I think I should probably put the +4. We do see +4. Right, so we do see +4 in some reactions, slightly when it turns to the brownish color. And cobalt, no, what is the normal common oxidation states of cobalt? +2 would be a normal oxidation state for cobalt. I don't think there's going to be many different oxidation states for cobalt that they wanted to put here, but it is for cobalt. Wait, cobalt +2, cobalt, you're gonna have more. Right, what are the cobalt states though? It's gonna be +2 and +3, right? So I think +3 is also stable for cobalt, and that should be fine. So you guys should be able to handle this, right?
Excuse me, sir. I understand why we put the elements before the rest of the configuration, but why are they there? I can see why it makes sense, but why are we writing it like that?
Oh, you
Instead
mean
of
like argon and
well,
krypton?
I guess it saves time. Yeah, I guess it saves
Okay.
time instead of just writing out everything.
Okay, why did I put them there?
I'm asking why would we write it like that, but I'm realizing that it would save us time rather than to write out the entire thing.
Yeah.
From
So it saves us time. Also, on the printed paper, it is written like that, so I just follow through written like that. That's like the main reason. I just follow through written like that. Plus, strontium would be so long.
Sir,
Go ahead.
sir, for chromium, sir.
Mm-hmm.
Sir, why did you not put the oxidation state of +2, sir?
It's a +2 oxidation state that we use. The most common oxidation states All right, so we normally see +3 and +6 oxidation states for chromium. Those are the most important states that we looked at for chromium. It is also stable as -2, right? And I think +2. So I guess we could write the +2 because we usually look at the. Let's use the +2. We could write the +2. Why I write just +3 and
Sir,
+6?
could you please scroll down?
Scroll down, meaning towards the
I want to
+2.
screenshot the table. Yes, sir, I want to screenshot the table.
Alright, so we have that there. So we generally use +3 and +6, but there is a stable +2 oxidation state for chromium, so sure. Alright, so we have that there.
I know this question isn't hard, but all of that for 5 marks?
They must be joking.
For 5 marks?
Well, for 5 marks, what they could probably be asking is just for one stable oxidation state. In that case, then this would be easy because all of them are generally stable at +2. So I would just write +2 for everything. So if it's asking for one, then sure. But I'll just write all the common ones just in case anything. Explain the difference between the trend in the first ionization energy of the group 2 elements and the first row transition elements. Go ahead. What would that be, that difference? Something like this could come tomorrow. Could. That doesn't mean it has to. But because it's transition elements. So explain difference.
Sir, group 2 would decrease down the group, and the transition elements, they would increase going across.
That's a very okay. Okay. That is true. For our first row transition elements, it is a period, therefore it will increase going across, while the group 2 will have the elements going down. Okay, so it's group versus period. Okay. So, but wait, let me find out how much marks this is for. Oh, okay, 4, just 4. All right. So we know that our group 2 transition metals would have higher ionization energies, or would it have lower ionization energies? Would it be higher or lower? Would be lower, right? Low, high, low, high. What is the difference? Group 2s. If we look at calcium and calcium. Go ahead.
Sir, it would be low because of the the radius, sir, the atomic radius.
So we know that atomic radius decreases going across a period. Therefore, right, when you look at the ionization energy of our group 2 metals, they would have a higher ionization, well, they would have, sorry, lower ionization energies, right, than that of their transition metal counterparts. Because we know that for our transition elements, right, the atomic radius decreases, but not really by that much. But we know that the nuclear charge is increasing along with them, so they have higher nuclear charge compared to that of their group 2 element counterparts, right? So due to that high nuclear charge and that smaller atomic radius is going to have a higher ionization energy compared to our group 2 elements, which will have a larger atomic radius, right, and a smaller nuclear charge, right? So you guys should be able to explain those stuff.
Wait, sir, can you repeat that, please?
Repeat in okay. So what we're saying is that as we go across period, the size of the atom gets smaller, right, and the nuclear charge increases. So those two things, when you think about the contribution to ionization energy, it will actually increase ionization energy. It makes it much harder to remove that electron, that outer electron, right? But with our group 2 now, they are fairly larger than our transition elements, right? And that increase in distance, right, is also there. Plus their smaller nuclear charge will actually influence ionization energy to be lower. Alright? So that's what we have there. 4 marks generally. And there are a lot of things you could state about those. Account for a difference in oxidation state between vanadium and calcium. Go ahead. Go ahead, guys. No, we don't know. All right. Orbitals. Calcium's outer orbital, the 4s orbital, is filled, right? And calcium's 4s orbital, right, has a low enough energy so the electrons can actually leave. So calcium most stable most stable oxidation state is actually the plus 2 because its 4s orbital only has 2 electrons. Therefore, when it's lost, we have plus 2. But when we look at something like vanadium that has a d orbital with multiple configurations, right? The d orbital itself, right, the unfilled d orbital, allows for multiple stable configurations of electrons, right? And each stable configuration of electron gives vanadium a different oxidation state. So this is why transition metals would have multiple stable oxidation states, right? Because the electrons in the unfilled orbital can be easily lost or easily gained, right? Allowing for different configurations, right, that can be stable, right? So as we said, for calcium, right, there's a filled 2s orbital, right? So there are not many configurations for calcium, and calcium's 1 plus oxidation state is unstable compared to 2 plus, right? So it's 2 plus is the most stable, right? Right? In the case of our transition elements, right, there is easy transition, easy loss and gain of electrons into their d orbitals, and there are multiple states in which the electronic configuration can result in stable oxidation states, right? So we can note that our group 2 metals, for example calcium, right, will not have multiple stable oxidation states, while our transition elements can have multiple stable oxidation states. All right, so we have that there.
Sir, can you write that down on the thing, please?
Well, it's recording, right? And I think I'm recording it so I don't have to like sit and use all the time to write the stuff down.
Okay, sir.
So I'm gonna send to you guys. Oh wait, your exam is in the afternoon, right? Okay, so it's in the afternoon. You'll have plenty of
Yes,
time to
sir.
review stuff. All right, so I'll get this recordings to you guys for that. Calcium carbonate is more thermally stable than magnesium carbonate. Explain. Somebody come and explain this. I went through an entire rant on group 2 elements. So let's explain this. Remember polarizability, distorting electron clouds on the carbonate ion. Speak about this. Speak about covalency, right, of the bond, so decreasing the level of covalency. Explain this to us. Why is calcium carbonate more thermally stable than magnesium carbonate? We have been doing so well. Let us continue.
Is it because of the polarizing ability of group 2 elements decreases going down because they're increasing in atomic radii? Therefore, it is
Increasing.
it's the opposite.
It's the opposite. Okay.
I'm honestly not sure.
Anybody else? Anybody has any attempts? Go ahead.
All right, sir. So calcium is lower in the lower down the group than magnesium. So calcium is more stable because magnesium, because its atomic radius is smaller than calcium,
Mm-hmm.
magnesium has a higher polarizing power than calcium.
Mm-hmm.
The problem with the polarizing power is that the polarizing power, it affects um so the higher the polarizing power, it kind of gives it like the bonds kind of become a little more ionic
Mm-hmm.
in a way, and versus the calcium, the polarizing effect would be lower and stuff. I don't know to really explain it better, but that's what I have.
Okay, so thermal stability speaks to whether or not the substances will decompose under high temperatures, right? The main thing that determines thermal stability would be the cation size and the charge density. Why is it the cation size? It is because both of them are carbonates, so anion size will not matter in this case, right? The smaller the cation size, right? The smaller cations have higher charge density, right? So it's leading to stronger polarization of the carbonate specifically, and the stronger polarization decreases covalency, right, of the bond between the carbonate and the metal itself, and allows for them to decompose easier, right? So it allows the bond to be broken between the cation and the carbonate ion, right, leading to that decomposition. So what we're saying is that the smaller the cation, the easier the carbonate's decomposition, and the smaller cation which will be which one?
Magnesium.
Magnesium.
Magnesium. Therefore, magnesium would be less stable than calcium, right? Because if we look at calcium, calcium is larger, has a larger charge. Well, mm, it has a smaller or high or lower charge density, right? So it doesn't lead to a high degree of polarization. So the bond has a little bit more covalency than that with magnesium carbonate, and allows for the stability under high temperatures. That is the answer to the question. All right.
Is it the same reason why the nitrates, why that is a trend in nitrates too?
Lovely. Yes, it is.
Okay, because I thought they were different. I thought one was increasing and one was decreasing. So both of them are increasing going down then.
All right. So if we look at the thing, we should be able to tell that information. Okay. Explain now the following observation in terms of stability constant of the complex ion formed. When concentrated hydrochloric acid is added to a pink solution of cobalt chloride, the solution turns blue. Come and explain this. Let's go. Nobody's stepping up to the plate.
Sir, all I know is in the presence of chlorine, cobalt turns from pink to, well, I think it was yellow, but oh no, that's copper. Never mind.
Okay, somebody raises their hand. Go ahead.
So sir, chlorine is a great oxidizer,
Interesting.
sir.
I'm just saying interesting. I'm not saying that it's wrong. Chlorine is an oxidizing agent, sure, but let's continue.
Okay. So sir, the chlorine from the hydrochloric acid would well, it would oxidize the cobalt. Wait, wait. Um, oh, it's cobalt chloride. Well, sir, there will be some repulsion between some ions which will cause.
Something will go on. All right. Anybody has an idea though before I answer this, or you just want to let me answer? Go ahead.
Sir?
Sir.
Oh,
Oh, you can.
okay. What I think happened is that because hold on, it becomes a tetrachloride. That's what happens to it.
Nope.
No.
Sir, would it displace the cobalt and the cobalt would form a precipitate?
Nope.
Cause no cobalt. Oh, John.
Sir, sir, would it like form like, all right, sir, so you add seal, sir, so it's trying to like get rid of the extra seal, right, sir?
Nope.
So like, would it go to
You're going to have hydrated. You're going to have some
CuH2O6
water.
CuH2O6 2 plus, sir, plus
Ah, I'm hearing it.
sir, plus so I don't remember what the next product is, but I know that it goes to CuH2
But that's
6 2 plus, which is blue, sir.
okay. So that's for this. That's for this reaction under here. But what is happening here? I heard that chloride is a good oxidizing agent, but in terms of stability constant, so therefore when you mention that chlorine is a good oxidizing agent, they will give you 0 marks, right? So what's happening here, guys? Question: when you see a color change, is that an indicator of a chemical reaction?
Yes, sir.
So something
Yep.
chemically has changed, right? So we have a now a pink solution of cobalt chloride, and we're adding hydrochloric acid to it, and it turns blue. When you dissolve cobalt chloride in water, what becomes of it?
Pink.
Sir,
Since water is basically a ligand, will it only substitute into the
Yeah, so what we're going to have is cobalt, well, X aqua cobalt being formed, right? So we're gonna have a cobalt complex with water and water alone. And when we have concentrated hydrochloric acid, it's going to displace, it's going to exchange the ligands, right? The water ligands, right? For chloride ligands, right? Because the chloride ligands are stronger field ligands than that of the water in that case, right? Or chloride, right? Cobalt's ability to form a stable complex with chloride, right? Is better than its ability to form a stable complex with water. So the stability of cobalt chloride complex, the tetrachlorocobalt, would be more stable than hexaaqua cobalt, right? And that would basically mean that the stability constant for the reaction is positive, right? It is high, right? So that the only reason for the only way a Lincoln exchange can occur if the stability constant is positive is high, right? So if it is high, that would mean that the cobalt chloride, not the cobalt chloride, sorry, the tetrachlorocobalt complex would be more stable than that of the hexaaqua cobalt complex, right? That is what's happening, right? So remember, when cobalt chloride dissolves in water, cobalt becomes hexaaqua cobalt, right? And that is a pink solution. This is why we use cobalt chloride paper to test the presence of water. It's the formation of this complex, which is pink, right? And now what we're doing, we're adding hydrochloric acid to the complex. We have a ligand exchange. So what does that mean for the stability constant? It means our stability constant is positive, and it means that our chloride ligands are going to be forming a more stable complex with the cobalt, more so than that are what more so than our water ligands, right? That is what we're talking about. And if we what we're asked now to do is to write our balanced equation for this, right? So what we have here is X aqua cobalt, so H2O, right? 6, 2 plus, right? And what's gonna be happening here? We're gonna add HCl, right? A balanced equation. Is this balanced equation supposed to show everything? In the case of the balanced equation showing everything, we should actually, what should we do? In that case, right, we should be showing 4 of these, right? Because now we need to actually stabilize the entire reaction, right? So what we're gonna do is end up with something like this now. we're gonna end up, that is really interesting. All right, so we're gonna end up with cobalt Cl4, right? So Cl4, well, so technically it would be Cl22, right? Cl22, so it won't be Cl24, right? Like this, right? And it's going to be, which oxidation state will it have? Will it still be positive 2? Well, let me see, actually. Okay, let me see. I would believe that it's actually this reaction that they want us to do. So let us just add, right, the chloride to it, right? So in the case where we add the chloride to it, we allow the water to remain, right? We allow H2, right? And in this case, we're gonna have H2O2, right? And open bracket, we're gonna have chloride. So chlorine. Um, well, we don't actually have to have the open brackets, right? So we can just leave it like this, to be very honest, right? So we can have it like this, and we can show that there are 4 chlorine atoms here, and then we can actually close this bracket and put the 2 minus ion. So that is what is being present here, plus the 2 water that we actually, the 4 water actually, that we actually lost, 4H2. So what's basically happening here is that we're gonna form this. So I think this is the one of the, this is probably what they want us to have, right? Which is our our diaqua tetrachlorocopalate, right? So that will be the name of this ion here, and this ion will be blue, right? So in this case it will be blue, and in this case it will be pink over here.
Sir, is that a 2 minus charge?
Here's a 2 minus charge. So when we have an anionic ligand here, what we're gonna end up with is calling it cobalate. That is it. So firstly, you're gonna have the first ligand exchange, right? The first set of ligand exchange. They actually give it 2 neutral charges, then a negative, then a 2 negative. So I just drew the entire reaction here instead of the stepwise process, right? Because stepwise process would have been what, 5 reactions you have to write. If they ever ask you stepwise, you have to write with all your reactions, right, continuously, which is not hard. Okay, so you have that there. That is not the end of the paper. That's crazy. All right, so here we have the vanadium rainbow. So the test of ammonium vanadates. So here we have the our vanadium rainbow here. So we need to know the oxidation states, right, of our vanadium and place them in. So this paper is actually great to tackle these transition element stuff. If we add a few cm cubes of 3 molar sodium hydroxide to a small amount of ammonium vanadate, right, followed by the following, right, 3 moles of sulfuric acid, what is formed? Do you guys know the
Sir
test?
Green.
Go ahead. Oh, it's a green?
Yes, sir.
Alright, so you're going to have something green being formed. Interesting. Okay, so green is it? What is going to be formed though? So we're gonna have the green. So you said you can have the green. What is the green? What's the oxidation state of green? For green.
Sir, +3.
3.
Right? And that is an example of the +3 oxidation state, right? A few pieces of granulated zinc would give us what? What would zinc do to it? If this is +3 though, interesting. Is this +3?
To blue. It'll then change to blue to green, then to blue, and then to purple. No lie.
The no lie.
Wait, wouldn't it be green first?
Repeat.
Wouldn't it change to green first, then blue, then green again, and then yellow, I think?
And then I think. All right, interesting.
The final color is purple.
Oh,
But
okay.
then you will have a state wherein it will have a mixture of both +4 and the +3, and then it will move to +3. There's going to be an intermediate stage where it's going to be moving between more than one state.
Okay, so hold on, right? So this is okay. So it changes to which color first,
Blue.
right? And you're saying that it's gonna change to blue. In that case, which oxidation state is for blue?
4.
+4, right? And we're gonna be going to which other oxidation states? What are the oxidation states we're going to? Is it 4, 5, 6? Is it 4, 5, 7?
The last one is 2.
It's going to be 2. So what we're doing, right? So we're reacting with that. So we're gonna be 4, right? So let's see. Let me ask So if the final one is 2, what are the intermediate ones?
Green and yellow.
Asking about the oxidation states, right? Not necessarily the color. I'm asking for the oxidation states, not the color here. So when we know the oxidation states that should be existing at different areas, then we're just writing the color for those oxidation states. Okay, so what's happening? What are we doing? We're adding the sodium hydroxide to the ammonium vanillate, right? So what's gonna happen here? Once we add acid to it, what's gonna happen? Guys, everybody's silent and I don't know why.
I
You
think we
know,
just
I just looked. Please.
The first one, let me erase everything because let's see. That first color form, when we add the 3 moles of sodium hydroxide and the 3 moles of sulfuric acid, what is gonna happen? What is the color that we're going to get? What do we have? Do you know the experiment? Do we know the experiment, guys? What we're doing, we're adding sodium hydroxide to ammonium vanillate, right? For us to allow, right, it to react under these basic conditions, right? Thing is now, if we add too much of the if we have that much of the sodium hydroxide, what we do, we add the acid, the excess acid to it, right? In order to neutralize, right, any amount of excess sodium hydroxide, right? What we're trying to do is isolate a specific oxidation state of vanadium, right? And this oxidation state of vanadium specifically, right? Would be what? Which oxidation state would that be? In ammonium vanadate, what is the oxidation state of vanadium in ammonium vanadate? You guys can find the oxidation state for this one. If ammonium is +1 altogether, and oxygen is -9 altogether, is -9 that? It's -6,
No,
right?
sir.
-6 altogether, right? Then this is what? Which oxidation state this? It's going to be what? Which oxidation state, guys? Plus what?
Sir, +5.
It's going to be +5. All right. So generally now, +5 is +5 a stable oxidation state of vanadium?
Sir, I don't think so.
Don't think so. Okay, let us see. Is it? Is vanadium stable as +5? Yes, it is going to be stable at +5, right? It will be. Okay, but what's going to happen here? Are we going to have changes in the oxidation state of vanadium? We want to know if it is the +4 oxidation state, which is blue, or the +5 oxidation state, which is yellow, which will be at the top here. That is my question to you guys. We need to understand the experiment, or we cannot get any vanadium questions right.
Sir, what did you ask?
What happens? What is the first step of our ammonium vanillate tests? Okay, so seems like we're just okay. It seems like everything is just interesting. Everything is just interesting. Okay, so what are we gonna do now? In dilute sulfuric acid, right? What we're going to get is VO2, right? That is going VO2 is present, and that's going to be our +5 oxidation state generally, right? And then we're gonna have reductions. Okay, right? So we're gonna end up with our in dilute acid. We're gonna have that. So what we do, we dilute the acid using sodium hydroxide here. What we're gonna have here is going to be some amount of vanadate, right? Sorry, not vanadil, right? Oxide or vanadium oxide, or what we call vanadia, right? We're going to have VO2 plus, which is +5. Then we're gonna reduce now to the +4, right? Then we're gonna have the +3. Then we're gonna end with the +2. All right. So what we're going to have here, the color formed generally, right? This is from my understanding. So if there's a different thing that you guys have been going through, Cape, let me know. But the test itself will produce these colors, right? I know that Cape tend to skew things, but I'm not sure whether or not Cape skew this, right? So what's gonna happen here is they're gonna have a yellow color there. Then the yellow will change to blue when we now start the rainbow. The start of the rainbow is generally blue. Some persons are saying that blue is a general start, right? The start of the rainbow is indeed technically blue, right? And then what happens now, we're gonna have blue to green, right? This is from my experience, by the way. And then from green, now what we're gonna have, we're gonna have a transition state, right? What's the transition state going to be? This is going to be purple. That's not how you spell purple. All right. We're gonna have purple at the end, right? But there's going to be a transition state where we have the existence of two ions. I know somebody was talking about it. Where are they now? What's going to happen? That state in between there, what is it going to be? We spoke about the state. What's the color of that state?
Is it violet?
You sure it's not green to blue and
Okay. So what are the oxidation states? That's my question. Because this is oxidation state plus 5, plus 4, plus, this should be, sorry, plus 3, right? And it should be plus 2. Those are the oxidation states now. So if it is going to pass through, is it that it's going to jump? It's going to go to plus 3 and then to plus 4? Explain to me how that works. I want us to understand the experiment. So what's happening here? Do we go neatly throughout the entire oxidation stage, or do we jump to one oxidation state before the other? What's happening here? Nobody has anything to say?
Sir, in the beginning of this paper, doing module 1 and module 2, I was like, this was so manageable. They had it so good in 2021. Then we started module 3, and I cannot answer anything. I am feeling like I'm going through psychosis. This is not, I hope this does not come on the exam tomorrow. This is so hard.
This is
Oh.
I have a strong feeling it will appear.
Okay, please.
I have a feeling everything when me do like so far I go come on the paper. That always happen.
Okay, so vanadium, right? I think this came on 2021. I don't think it came on any paper since. So multiple oxidation states will exist.
So we might get it if we not come on the paper since 2021. There's a possibility that we might get it.
There's a possibility, yes. The thing is now that mixture state that we've been talking about, I'm honestly throwing out that mixture state there, that allegation of a mixture state, because generally a mixture state will only occur if there's uneven reduction. Right? So what would be this? That color in between there. Because there are generally this amount of steps there now. So why the about next step there? Okay. So what we're going to have is an actual typical greenish color, right, in between. Because what we're saying, if there's going to be a mixture of the plus 3 and the plus 2 oxidation state in this area, it's going to be an intermediate between purple and green, right? And that would generally be the intermediate there. Let me have a. Oh, there are way more questions to this. Okay. I mean, it's just the species that we need to add, right? So, that intermediate state that we're talking about, it will have to be a mixture between green and purple. So it might be a greenish purplish color that may appear there. Honestly, I may have to recheck what is happening in this question, because it's honestly
So sir,
way more interesting than I thought. Go ahead.
sir, when I was studying, sir, I read something about before you reach the plus four oxidation state, there's a mixture between the plus five and something else to produce a green color. So that's why this is confusing me right now,
Okay.
because I did not learn anything about this.
Okay. So you're saying there's a mixture of plus five oxidation state that gives a greenish color.
Yes, there's a thing before you reach the plus four oxidation state, which produces a green color.
Okay, so it's the position of where our colors are. It's the issue then. Hmm. So if we mix the yellowish and the bluish color here, that would be from ammonium metavanillate generally. Hmm. But what is mixing? Because we need to know what is mixing, because if we're going to be writing, we'll be completing this section, we need to know all the species. So it's a mixture of the plus five oxidation state and what that gives that green color. Can anybody let me know what that is? All right. So there can be a mixture between the yellow and the bluish oxidation states that would give the green. All right. Give me a moment. Right. So if there's a mixture of the yellow and blue, we can actually get a greenish color. All right. So with that, then let's move down everything and put the green here. Right. It would probably be due to some uneven up reduction, because if uneven reduction takes place, what I mean by uneven reduction, it means that some are reduced faster than others, right, or more than others. You can actually have the occurrence of a green precipitate. Why? Because if we overlap the colors of light of green and, well, of yellow and blue, we can actually get a greenish color. So it leads me to believe that that notion, right, may be where the mixture comes in. So in that case, what we're gonna have is there. So the information, where we get that from, that book or piece of information, could we have a look at it, please? So could you send it in the group? Because I need to have a look at that information. Because technically, if the two oxidation states exist at the same time, it will be a greenish color. And that would be if the plus 5, right, and the plus 4 existed in the same time. All right. All that's really asked of us down here is really just to state the color and formula of the species, right? So all right, so Jordan has that there. Okay, lovely. So in the case of that now, what we have to do is generally just write the species, right, that we have here, right, and the different colors. So we don't really, yeah, so we just need to write the colors out of the species here. Okay, so in this case, what are we going to have for these now? We're going to have the color, which color would it be? The color yellow is attributed to actually the VO2 plus, right? The color, you'd have the color like blue. Blue will be
What topic under module 3 is this?
Transition elements. It's under the topic of transition
Okay.
elements. VO plus, or this would be 2 plus, VO2 plus, right? The color for green, right? That would be, green would be what again? That would be like in vanadium sulfate, right? And in the case of vanadium sulfate, this would be a plus 3, so it would generally just be the plus 3 species causing this color, right? If we have a violet color or a purple color, PLE, the purple color would be due to the 2 plus ion. This is 4 marks, right? If we give the yellowish green, let me just write yellowish green from above, the yellowish green mixture. If you have a yellowish green mixture, what it's going to be is a mixture of the VO2 plus and the VO2 plus. Alright, and that